This is a presentation from Group 2, Jonas, Mobina, and Ebba for signal processing. We have decided to work on an ECG signal for this presentation. An ECG signal is the process of producing an electrogram of voltage per time of the heart's electrical activity. This is done by applying electrodes on different locations on a person's skins, but in short, a way to measure a person's heart activity. In medical field, this is used to compare to an this signal is used to compare it to an ideal to detect if it's any disease or abnormalities. In image 1, it is it's a picture of an ideal ECG signal. So this is what we're expecting to get after filtering our data. Image 2 shows our signal, our raw data that we have collected for a measured period of 20 seconds. And you can distinguish some of the characteristics of the ECG. It can seem that it's noisy, and well, it's because it's raw data and it doesn't have any filters on it. And lastly, image 3 shows our filter domain, frequency domain diagram of the same data. 5 different recordings to measure and compare them with one another. And by comparing, I mean that compare the original data that we got and compare it to the final results that we had, which is a filtered signal. The first image shows our time domain, the signal in time domain, which was originally collected from the database, and using MATLAB and changing some codes, we converted the first image to the second one, which is a frequency domain. During this process, we faced some challenges, including removing the 50 Hz noise, which is visible in the second figure in frequency domain. This 50 Hz noise is a very common problem in ECG signals, and it's called the power line noise, and it's almost in all ECG signals. Removing this and filtering out this signal was a little bit challenging for us. The second challenge that we faced during this time was removing and smoothing the signal and basically high and low frequencies.
So the first plan for our research for this project was to reducing as much noise as possible without removing too much of the vital part of the signal. Also, what type of filters are the most effective, which filters are cheapest, most expensive, and looking more at the type of how to build like an ECG in real life and watching the different types. And also how we can filter out our signal to the extent that we can compare it to an ideal heartbeat wave. We realized pretty quickly that an ideal heartbeat wave is not possible on a human heart because humans are not machines and they are not ideal. We also realized that reducing as much noise as possible without removing too much of the vital parts of the signal was also a bit of a challenge. Because either you remove too much or too little for it to be any difference. So that took us quite a while, which meant that our research question for types of components and physical stuff for the filters, we did not have the amount of time, and we wanted to be more focused on the MATLAB part of it. So we changed up our questions during our project and started to be as the first one at reducing as much noise as possible, but also the effectiveness of different types of filters and their characterization in MATLAB, because it's pretty different from real life, and how we can compare MATLAB system to an ECG physical machine. So we quickly realized that the filters in MATLAB were both better and in some parts not as effective as in real life. The description of the signal processing method in this project is a single lead ECG. So the person who did these measurements used a single lead ECG, which is measurement to use an electrode on the skin and measures potential difference between usually the right hand and the left hand. In this, they use a limb clamp to imitate the interaction with the identification system, and it's easy to handle. They also use a 1500 hertz sampling frequency, and it's suitable for it allows us to catch the quick changes during the period of a heartbeat. And we need to be able to catch electrical changes to identify our signal. We expect to have a noise ECG signal, but somewhat still distinguishable as an ECG signal, being able to see the R peaks and some of the segments that characterizes ECG signals. And with proper filtering, we will be able to see all of the different intervals and segments from start to stop. And the reasons for the people in database to use this method is it's easy, it's cheap, and it's easy because it doesn't matter where on the body you put it because it's so light and it's just one electrode, so you don't have to mix with like several different kinds.
The result we got in time domain, as you can see in the images, where we have the first two are our unfiltered version in a 2-second period and the entire 20-second spectrum, whereas the two below show after filtering. What we did was first we removed the baseline drift, as you can see in the 20-second unfiltered version in time domain, or image 2. You can see that the wave is a wave. It's not it doesn't follow the X-line as it should. This occurs due to, for example, just movement during the sampling. For example, breathing, and that can't really be avoided since you have to breathe. And so we had a high-pass filter, which is one of the most common ways to eliminate the baseline drift. And as you can see in the image below, we got it to follow X-axis almost perfectly. So it was a really good solution there. Next, we also wanted to remove the graph or the signal fluctuated so much. Meaning with that is that it goes up and down a lot. So we used a moving average value instead, which is a process called smoothing. So we smoothed the line and dampened each value with taking a average value around that instead and putting it in and plotting it, which gave us a more accurate view and a much more readable view where you can compare it to the ideal ECG signal below and see that you have the R peaks, you have the different segment, the T wave, the P, and the, for example, QT segment. Although not perfectly, but you can. It is clearly readable from the graph. And in frequency domain, we have you can see that our signal is dominated mainly by the low frequencies when it's unfiltered, but it also has the 50 hertz, which is a really common thing that almost always occur when you have electrical instrument usage, and it's something that really can't be avoided. So we have to work around it with filtering. So for the filters, we know that when we're working with ECG, we want to have the low frequency left because a heartbeat doesn't really have a high frequency, maybe around like 4 hertz. So everything above a certain threshold needed to be removed. So we wanted to use a low pass filter for that. And we also wanted to remove the 50 hertz using, for example, something called a notch filter. And both the low pass and the notch filter were done in a similar way using a Butterworth filter, but with different cutoff frequencies. So for our low pass filter, we use a Butterworth filter of order number 4, which is, as you can see in the image, has a really good step off, or I think it's called roll off with dampening amplitude. So we wanted to use an order that could produce it really well, but not overly complicate the filter. So order number 4 sufficed, and then we use that in a Butterworth filter again for the low pass filter, and also again with the notch filter. The notch filter was a butterworth filter with a cutoff frequency from 48 to 42, so everything in between got removed, and as you can see in the lower graph, it completely removed that, and the low pass filter managed to remove all the unnecessary frequencies from around 40 Hz. What we ended up with was close to an ideal representation of an ECG signal, although we do not think it's perfect. We still think it's good enough from what we expected, and we're really happy with what we got. How about research questions? We think that we managed to achieve our goals. We managed to get almost an ideal ECG signal, although there's still room for improvement and getting to know and understanding the filters in MATLAB function and how they work, what inputs they need and what outputs they need, for example, is something that we still need to understand more, and for us to be able to do this better in the future if it were to be done. And that goes into what we could have done better. It's always easy to say that when you're first learning something, it's easy to look back at, oh, why didn't I do this from the start? But in MATLAB, there's so many filters and different functionalities that it is a bit overwhelming in the beginning, and you find something that you think works, you will try it, and then you will find something better, and then you try that, and so it was just a lot of trial and error for us. Try different methods, try different filters, call different functions. We work with the other programs that MATLAB have that can design filter for you and use them. So that's something that we learned, and is something we will take with us when working with the other projects in, for example, MATLAB, that we have this knowledge and we know now what different functions do and how we can filter, so we can focus on other stuff as well during that project. Otherwise, the project has gone really well, and everyone's been working really well together and in unison and helping each other out to understand and giving feedback. So we're happy with this project, and we think we achieved what we wanted to achieve. Thank you very much for listening.